Our transformation to a rotating frame of reference has introduced us to the concepts of Coriolis, geopotentials, and the geostrophic balance, which is the leading order dynamical balance of Earth's oceans and atmosphere. We have seen that this geostrophic balance is between the horizontal pressure gradient and the Coriolis acceleration, Fu, where F is the Coriolis parameter, which is 2 times the local vertical component of the rotation vector, omega sine theta. This balance can be written in vector form as 2 omega cross u is equal to the grad of the pressure on density.
Here we ask what happens when the pressure gradient is not sufficient to balance the Coriolis acceleration. As is often the case for objects or projectiles or Lagrangian drifters in the oceans or atmosphere. Consider an object of mass m moving with a velocity u at some latitude theta. The Coriolis acceleration is going to be Fu, which we can multiply by the mass m to get the Coriolis force. Now, we say this is a force, but in reality it is an inertial force or a fictitious force because it is only apparent in the rotating frame of reference. The force is reference dependent. The direction of this Coriolis force is always normal to the motion of the object, so it slightly deflects the object from its trajectory. The Coriolis force remains normal to the motion of the object, so the force too will be slightly deflected. This leads to the object following a curved path. There is another type of force that we know of that is directed normal to the motion of an object, the centripetal force, which is m times u squared on r, where r is the radius of curvature. Now, we can treat the Coriolis force as if it is a centripetal force and calculate just how curved the path of the object is going to be. So we take the centripetal force as equal to the Coriolis force, and we cancel for mass to get the accelerations, which we can cancel the velocity on the right hand side, giving us u on r is equal to f. So r here is u on f. This is useful. We have now calculated the curvature of the trajectory as a function of the object's velocity and the local Coriolis parameter. For large velocities or small f, like at the equator where f is 0, the radius of curvature is large, meaning the deflection due to the rotation is small. For small velocities or strong f, the curvature is small, so the deflection is substantial and results in the object following a circular trajectory. This is referred to as an inertial oscillation. Now, given this radius of curvature r and the object's speed u, we can estimate the time that it takes for the object to loop around on itself as the circumference of the circular path, 2 pi r, divided by the object's speed, u, giving us t, the inertial period. And now 2 pi on the period is the inertial frequency, f. So as a consequence of these inertial oscillations, the trajectory of objects moving on Earth tend to be cyclotic rather than straight. This motion is obvious in drifter trajectories, such as these surface drifters from the North Pacific Ocean. Here, each oscillation along their path takes place over an inertial period, roughly 1 day, so that each individual path should have about 30 loops, given that there's 30 days of data shown here. We can also see this oscillatory behavior in the lab, here in the movement of particles on the surface of a rotating fluid. It's worth noting the parallels between the inertial oscillations that we've investigated here and the cyclotronic dynamics of plasmas.